Hi students, in this video I am going to talk about the concept of conditional expectation, joint moment generating function and their properties and some related applications. Okay, conditional expectation. Let me give some intuition. In a class, for each student, let us associate two numerical characteristics x and y, where x denote the mother income, y denote the father income. The next y is going to be bivariate random variable. Okay, if I take g of xy to be x plus y, then this g of xy denote the family income of the student. Okay, then expectation of g of xy denote the average family income. Average family income of the class. Okay, we know this. Now, what if you are interested in average family income of the students whose mother income is fixed to something like 10,000? This is something called conditional average. You can say conditional expectation. That's what we are trying to define now. Okay, fine. For a bivariate random variable xy, the conditional expectation of g of xy given y equal to y denoted by this defined to be this summation if xy is discrete type. What is the summation? Summation of g of xy px given y of x given y, where sum runs over x belongs to Sx. Here this px given y is conditional PMF of x given y. So this sum is weighted sum of g of xy values with the weights being corresponding conditional PMF of x given y values. Here sum runs over x belongs to Sx and y is fixed to given y. So this sum will be in terms of given y. Okay. So this is the conditional expectation of g of xy given y if xy is discrete type. Okay. Similarly, if xy is a continuous type, with conditional expectation of g of xy given y defined to be this integral. This is the integral of g of xy fx given y of x given y dx. Okay. Here this fx given y is conditional PDF of x given y. As y is fixed to given y, this integral is going to be function of x only. So we are integrating with respect to x. This integral value will be in terms of given y. Okay, so this is the conditional expectation of g of xy given y if xy is continuous type. Okay, of course, we say this conditional expectation of g of xy given y exists provided the sum or integral converges absolutely. Okay. Similarly, we can define conditional expectation of g of xy given x equal to x. Okay. Fine. Next. Okay. Let's do an example. Let xy be a continuous bivariate random variable with a joint PDF f of xy equal to e power minus x by y times e power minus y by y for x positive, y positive, 0 otherwise. Compute expectation of x given y equal to y. This look like an expectation of g of xy given y equal to y, where g of xy happen to be x only. Okay, so we know how to compute expectation of g of xy given y, right? So this is going to be integral of g of xy, that is x, times conditional PDF of x given y, okay, dx. Here integration with respect to x. Okay, so first of all we need conditional PDF of x given y. What is given is joint PDF. Okay, what is the conditional PDF of x given y? It's going to be joint PDF of xy by marginal PDF of y. So first of all we need to find marginal PDF of y. How do you get the marginal PDF of y? Integrating joint PDF with respect to x, right? So the marginal PDF of y, so integrating joint PDF with respect to x, your x limits are 0 to infinity. As we are integrating with respect to x, So e power minus y by y kind of a constant. I can write this one out of the integration like this. Okay. Now we have to perform this integral. Okay. So integral of e power minus x by y with respect to x going to be this one, e power minus x by y by minus 1 by y. So if you apply these limits, it's going to be limit x tends to infinity e power minus x by y by minus 1 by y. If you apply 0, it's going to be 1 by minus 1 by y. Okay. Here, as y positive, limit of e power minus x by y going to be 0 as x go to infinity. So this limit is going to be 0. Okay. So now, so here this y cancel, minus minus plus. So you end up with e power minus y. So fy of y equal to e power minus y for y positive. Now we got a marginal PDF of y. Now let's write down conditional PDF of x given y. Let me clear this. Now the conditional PDF of x given y is joint PDF of xy by marginal PDF of y. This e power minus y cancel. So we have 1 by y e power minus x by y for x positive. This is the conditional PDF of x given y. Now we got conditional PDF of x given y. Now let's compute expectation of x given y equal to y. So this is going to be what? Integral x. The conditional PDF that we got is 1 by y e power minus x by y. Integration with respect to x. X limits are 0 to infinity. Okay. So let's find out this integral. Okay. Here, what I do, let us take a substitution t equal to x by y. Before that, let me multiply and divide by y. As we are integrating with respect to x, y is kind of a constant here. Okay. Then dt going to be equal to dx by y. Okay. So I can write this one y integral x by y t e power minus t dx by y, that is dt. Okay. And with this relation, t limits also going to be 0 to infinity because y is positive here. So this t I can realize as t power 2 minus 1, so that this integral can be seen as a gamma integral. So I can write y gamma of 2. So it's going to be y 1 factorial. Okay. So what we got? Y. So therefore expectation of x given y equal to y is y. Okay. So this is the conditional expectation of x given y equal to y. Fine. Next. The note 1, expectation of a g of xy equal to expectation of conditional expectation of g of xy given y. First of all, let me make sense out of this expression. The left hand side expectation I want to call joint expectation, because here I am going to use joint PDF of xy to compute this expectation of g of xy. Here the right hand side, this one, conditional expectation of g of xy given y. Here we use conditional PDF of x given y to compute this expectation. Okay. And this conditional expectation of g of xy given y is going to be the value dependent on given y. So this can be seen as function of y alone. Okay. So let me call it g1 y. So this whole thing I can see as g1 y, then expectation of g1 y. So this is like a univariate expectation of g1 y, because here we are using PDF of y to compute expectation of g1 y. Okay. So this is the meaning of this expression. So I'm going to show that this joint expectation of g of xy is going to be univariate expectation of conditional expectation. Okay. Before I prove it, let me give some intuition here. Let us say I have a 20 students in a class who is sitting in 4 rows and 5 columns like this. Okay, this is the 1 location, 1 2 location, 1 3 location, and this is like a 4 5 location. You get the idea. Okay, here I have a function for each ij, for each location ij, it will take the value which is the weight of the student who is sitting in ijth location. Okay, so if you want to get the average value of g, what you can do is you sum up all these weights. Okay, I from 1 to 4, j from 1 to 5 divided by 20. This is the one way you can get average weight of the class. There is another way you can get this average weight of the class. What you can do, first you get the average weight of the first row. This is conditional average because this is the average weight of the students who is sitting in the first row. Similarly, you get the average weight of the second row. Okay, then you get the average weight of the third row, then you get the average weight of the fourth row, then you take average of these 4 conditional averages. Okay, so average of conditional average is going to be total average, right? That's why here joint expectation of g of xy is going to be univariate expectation of conditional expectation of g of xy given y. Okay, so okay, let me clear this first. Let me prove it for a continuous bivariate case. Similarly, you can prove it for discrete bivariate case. Okay, let me start with the left hand side. Expectation of g of xy, by definition, this is a double integral of g of xy f of xy dx dy. Here first let us integrate with respect to x, then we integrate with respect to y. Now we multiply and divide by PDF of y here. Fy of y we multiplied and divided. Okay. Now this joint PDF by marginal PDF of y is going to be conditional PDF of x given y. This integral you can see as conditional expectation of g of xy given y equal to y. Okay. So now we have integral of this conditional expectation of g of xy given y equal to y fy of y dy. We know that this conditional expectation depends on given value of y, right? So this can be seen as some function of y like this, g1 of y. So now this look like integral of g1y fy of y dy. So this look like expectation of some g1y. Okay. What is g1y here? This one, right? So g1y I can write conditional expectation of g of xy given y. Okay, that's why this joint expectation of g of xy is going to be univariate expectation of conditional expectation of g of xy given y. Okay, here this expectation using distribution of y and this expectation using conditional distribution of x given y. Okay, similarly you can also show that this expectation of g of xy also same as this expectation of conditional expectation of g of xy given x. Okay, here this outer expectation is using the distribution of x, inner expectation using conditional distribution of y given x. Okay, fine. Next, note 2, variance of g of xy equal to expectation of conditional variance of g of xy given y plus variance of conditional expectation of g of xy given y. Let's prove this. First, let me consider conditional variance of g of xy given y. So how do we compute the variance of some random variable? Let us say some variance of some random variable z what? Expectation of z square minus expectation of z whole square, right? If you think this whole thing as some random variable, then it should be what? Expectation of g of xy whole square given y. Don't put square here because it's not a division thing, it's a given thing, minus expectation of g of xy given y whole square, just following this rule. Okay, so I can write this conditional variance of g of xy given y like this: expectation of g of xy whole square given y minus expectation of g of xy given y whole square. Okay, now if you take expectation both sides, so the left hand side is going to be expectation of this conditional variance of g of xy given y, and this one is going to be expectation of conditional expectation of g of xy square given y. So this is a univariate expectation of conditional expectation of g of xy whole square given y. So by note 1, this is going to be what? Joint expectation of g of xy whole square. Okay, because in place of g of xy, we see g of xy square. No problem. Okay, so you can use note 1. This is going to be as it is. So in the next step, we are going to write this one as it is, this one as it is, but this get replaced by expectation of g of xy whole square by note 1. Let me call it a. Okay, so this part we got as this one. Okay, a. Now let me consider this part, variance of conditional expectation of g of xy given y. Again, following this rule, I can write, if you think this whole thing as some random variable z, we should write like expectation of z square minus expectation of z whole square. So it should be expectation of conditional expectation of g of xy given y whole square minus expectation of conditional expectation of g of xy given y whole square. Okay, square for whole thing. Okay, again, for this inside part, again I can apply note 1. This look like a univariate expectation of conditional expectation of g of xy given y. So this should be equal to expectation of g of xy, joint expectation of g of xy. Anyway, we have whole square. Okay, so in the next step, I'm going to write this one as it is, this one as it is, but this get replaced by expectation of g of xy whole square. Okay, so this part we got like this. Now let us add a plus b. If you add a plus b, this one get cancelled. The right hand side we will be left with expectation of g of xy whole square minus expectation of g of xy whole square. Again, by following this rule, we can write variance of g of xy. Left hand side we have this one plus this one, that is expectation of conditional variance of g of xy given y plus variance of conditional expectation of g of xy given y. Okay, so this is what the note 2. Therefore, so we have this variance of g of xy equal to expectation of conditional variance of g of xy given y plus variance of conditional expectation of g of xy given y. Okay, similarly we can also show like this: variance of g of xy equal to expectation of conditional variance of g of xy given x plus variance of conditional expectation of g of xy given x. Here we are conditioning on y. Instead of conditioning on y, you can also condition on x. Okay, so in the same way you can show this. Okay, fine. Okay, let's do a problem. Suppose that by any time t, the number of people that have arrived at a train depot is a Poisson random variable with a mean lambda t. If the initial train arrives at a depot at a time that is uniformly distributed over interval 0 to t, This time is independent of when passenger arrives at a depot. Okay. What is the mean and variance of number of passengers that enter the train? Okay, let's do this. Let for each t greater than or equal 0, n of t denote the number of passenger arrivals by the time t, and y denote the time at which train arrives at a depot. Okay, then n of y will denote the number of passenger arrived at a train depot by the time train arrives. So this many people will enter into the train. Okay, here we are interested in expectation of n of y and variance of n of y. Okay, let's do this. Here it is given that y follows uniform distribution over the interval 0 to t, and number of passenger arrivals by the time t is a Poisson random variable with a mean lambda t. So n of y given y equal to t follows Poisson distribution with a parameter lambda t. Okay, see, if you think this is a, this is b, for uniform random variable, expectation is going to be what? A plus b by 2, and the variance is what? B minus a whole square by 12, right? So we can immediately write expectation of y as t by 2 and variance of y as t square by 12. And for Poisson random variable, mean and variance both equal to parameters. So the expectation of n of y given y and variance of n of y given y both equal to the parameter lambda times y, whatever y value may be. Okay, fine. Now, expectation of n of y by using note 1, it's going to be univariate expectation of conditional expectation. So I can write this expectation of conditional expectation of n of y given y. This conditional expectation of n of y given y, we know that is lambda y. So we can write in the next step expectation of lambda y. Lambda will come out. So lambda time expectation of y, and expectation of y we know t by 2. So it's going to be lambda t by 2. So therefore expectation of n of y is lambda t by 2. Fine. Okay. Next. Using note 2, the variance of n of y we can write expectation of conditional variance of n of y given y plus variance of conditional expectation of n of y given y. We know that this equal to lambda y, this also equal to lambda y, right? So it's going to be expectation of lambda y plus variance of lambda y. So this one we can write lambda times expectation y. This one we can write lambda square times variance of y. Okay, and expectation of y we know t by 2, and the variance of y we know t square by 12. So the variance of n of y is going to be lambda times t by 2 plus lambda square times t square by 12. Fine. Okay, next. Joint moment generating function we write as JMGF, read it as joint MGF. Okay, joint MGF of bivariate random variable xy denoted by this, which is a function of two real variables t1, t2, and defined to be expectation of e power t1x plus t2y. Okay, we know what is the meaning of expectation of g of xy, right? Here our g of xy is e power t1x plus t2y. Okay, so we say this joint MGF exists provided this expectation exists in the neighborhood of 0. That means we should be able to find some circular region around 0, 0 in which this expectation exists. Okay, fine. From this, we can easily see that this joint MGF value at t1 comma 0 going to be MGF of x value at t1. Because from above definition, this joint MGF value at t1 comma 0 going to be expectation of e power t1 x plus 0 y is nothing but expectation of e power t1 x. So this is MGF of x at t1. Wait a minute. Isn't it supposed to be joint expectation? Question is, for a function of univariate random variable x, is joint expectation same as univariate expectation? Okay, what I mean is, if you take a function of x, let us say g of x, expectation of g of x means, we mean this integral of g of x and pdf of x dx. But this g of x can also be seen as function of xy. Though it doesn't depend on y, still we can see as function of xy. So as a function of xy, this expectation of g of x should be this double integral g of x and joint pdf dy dx. First we are integrating with respect to y, then x. Okay, so from this we can write, first I can get this g of x out of the first integral, as we are integrating with respect to y first, then integral okay. Now we know that this is exactly the pdf of x. If you integrate the joint pdf with respect to y, you will end up with pdf of x, right? So this is exactly pdf of x. So now you see these two are same. So for a function of univariate random variable x, joint expectation will be same as univariate expectation. So that's why this makes sense. Similarly, the joint MGF value at 0, t2 going to be same as MGF value of y at t2. This is how we can easily get marginal MGF of xy from joint MGF. Okay, fine. Now let me talk about joint MGF of k-dimensional random vector. Joint MGF of k-dimensional random vector x under bar, which is a vector of k random variable x1, x2, xk, denoted by this mx under bar of t, where t is vector in Rk, okay, is defined to be expectation of e power summation tixi from 1 to k, okay, provided this expectation exists in the neighborhood of 0 vector in Rk, okay. So this is a generalization. We can also write this joint MGF in vector notation like this. Okay. So the joint MGF of x under bar at t we can write as expectation of e power t transpose x under bar, where t is this column vector, or you can say column matrix t1, t2, tk, where x under bar is this column matrix, or you can say column vector x1, x2, xk. Here this t transpose x under bar nothing but dot product. As a matrix multiplication, we can write t1 x1 plus t2 x2 plus so on tk xk. Okay, so that's why this is exactly this one. Okay, so joint MGF of x under bar at t going to be expectation of e power t transpose x under bar, which is a compact notation. This expression look much like a MGF we defined in the univariate case, right? Fine. Okay, next. Here is a continuous bivariate random variable with a giant period of f of xy equal to e power minus 5 for 0 less than x less than y less than infinity, 0 otherwise. Okay, let's find out giant MGF of xy. Then let us write down marginal MGFs of x and y. Then let us try to see if we can recognize probability distributions of x and y by looking at marginal MGFs of x and y. Okay, first of all, here the support of xy going to be this part, this region. This is y equal to x. Okay, this region. Okay. Fine. Now, the joint MGF of xy by definition is what? Expectation of e power t1x plus t2y, which is going to be double integral of e power t1x plus t2y f of xy dx dy. Fine. Here, if I integrate with respect to y first, then the y limit is going to be x to infinity, then x limit is going to be 0 to infinity. So here The y limits are x to infinity, x limits are 0 to infinity. Here this e power t1x plus t2y, I am writing e power t1x times e power t2y. This giant PDF replaced by e power minus 5. Okay. Now, as we are integrating with respect to y first, so we can get this e power t1x out of the first integral. So I can write e power t1x, and this is going to be e power t2 minus 1y. Now, integral of e power t2 minus 1y with respect to y is going to be e power t2 minus 1y by t2 minus 1. Now we have to evaluate this limits x to infinity. So this is going to be integral 0 to infinity e power t1x. Now the limit y tends to infinity e power t2 minus 1 y by t2 minus 1 minus at x e power t2 minus 1 x by t2 minus 1 dx. Now this limit exists only when t2 minus 1 less than 0. As y go to infinity, this e power t2 minus 1 y exists only when t2 minus 1 is negative, and that to the limit going to be 0. Okay, so this is going to be 0. Now, so we have to perform this integral. Next, now here if I get this minus 1 by t2 minus 1 out, so e power t1x times e power t2 minus 1x going to be e power t1 plus t2 minus 1x dx. Fine. Now integral of e power t1x plus t2 minus 1x with respect to x going to be e power t1x plus t2 minus 1x by t1 plus t2 minus 1. We have to evaluate at 0 to infinity. So this is going to be minus 1 by t2 minus 1 limit x tends to infinity e power t1 plus t2 minus 1 x by t1 plus t2 minus 1 minus at 0 it's going to be e power 0 1 by t1 plus t2 minus 1. Okay, fine. Now this limit exists only when t1 plus t2 minus 1 less than 0. Okay, and that to that limit going to be 0. Okay, so this limit exists only when t1 plus t2 less than 1, and the limit also going to be 0. So this is 0. So now we can write like this. Okay, this one we can write 1 by 1 minus t2, and this one we can write 1 by 1 minus t1 minus t2, because we have minus here, so joint MGF going to be 1 by 1 minus t2 times 1 minus t1 minus t2. This makes sense for t1 plus t2 less than 1 and t2 less than 1. So what is this region? Let us say this is t1 plus t2 equal to 1, and this is a t2 equal to 1. So this region. Okay, so we have some neighborhood around 0, no problem, fine. So joint MGF exists in the neighborhood of 0 0. So this is our joint MGF. Fine. Okay, next let's look at MGF of x at t1. It's going to be joint MGF value at t1 comma 0. If you substitute t2 value 0 in the joint MGF, we end up with 1 by 1 minus t1, which makes sense for t1 less than 1. So like this. Okay, so in this neighborhood it is guaranteed. So MGF of x exists, and it's going to be 1 by 1 minus t1 at t1. Okay, similarly MGF of y is going to be joint MGF value at 0 comma t2. So if you take the t1 value 0, you will end up with 1 by 1 minus t2 times 1 minus 0 minus t2, which is going to be 1 by 1 minus t2 whole square. So this makes sense for t2 less than 1. Okay, now by looking at these MGFs, I can say that x follows exponential distribution with the parameter 1, because here lambda equal to 1, right? And y follows gamma distribution with the parameter 2 comma 1. Here lambda is 1 and alpha is 2. Okay, fine. Next. Finding product moments through joint MGF. What is joint MGF? Mxy t1 t2 equal to expectation of e power t1x plus t2y. Let's perform partial derivative of order r plus s with respect to t1 r times with respect to t2 s times. Okay. The right hand side differentiation can be performed inside expectation. The reasons we discussed in the univariate case, similar reasons holds here. Okay. So we can actually perform this differentiation inside expectation, and this partial derivative of e power t1x plus t2y of order r plus s is going to be x to the power of r, y to the power of s, e power t1x plus t2y, as we are differentiating with respect to t1r times with respect to t2s time. Okay. Now, if we evaluated 0, 0, it's going to be expectation of x to the power of r, y to the power of s, which is exactly non-central product moment of order r comma s. This is how we can get product moments of all orders through joint MGF. Okay, fine. Next, in particular, expectation of x. Here, expectation of x can be seen as expectation x to the power of 1, y to the power of 0. This is nothing but mu dash 1 comma 0. So, r equal to 1, s equal to 0. So, which is going to be dou mxy by dou t1 at 0, 0. Similarly, expectation y going to be dou mxy by dou t2 at 0, 0. And the variance of x, which is going to be expectation x square minus expectation x whole square. Again, this expectation x square we can see as expectation x square y to the power of 0. This is nothing but mu dash 2 comma 0. Okay. So now here r equal to 2, s equal to 0. So it's going to be dou square mxy by dou t1 square at 0, 0 minus, again expectation x is this whole square. Okay. So this is going to be the variance of x in terms of joint MGF. Okay. And similarly the variance of y going to be this. Okay. Similarly, expectation xy, here r equal to 1, s equal to 1, so which is like a mu dash 1, 1. So it's going to be dou square mxy by dou t1 dou t2 at 0, 0. This is the expectation xy. So the covariance of xy is what? Expectation xy minus expectation x, expectation y. We have everything in terms of joint MGF. So the covariance of xy, we can write expectation xy is this minus expectation x, we have this, times expectation y, we have this. Okay, so this is how we can answer covariance of xy also through joint MGF. This is how we can get all these things through joint MGF of xy. Okay. Theorem: x and y are independent if and only if joint MGF of xy at t1 t2 equal to MGF of x at t1 times MGF of y at t2 for all points t1 t2 in R2. Here we are going to prove it only in one direction, that is x and y are independent implies joint MGF of xy equal to product of its marginal MGFs, but other direction we are not going to prove it here. Okay. Proof. Let x and y are independent, then we are going to show this. Okay. Let me start with the left hand side. Joint MGF of xy at t1 t2 by definition expectation of e power t1x plus t2y. This e power t1x plus t2y we can write e power t1x time e power t2y. Here e power t1x, which is a function of x alone, can be seen like a g of x. Here e power t to y, which is a function of y alone, can be seen like a h of y. Then this look like an expectation of g of x time h of y. When x and y are independent, expectation of g of x time h of y going to be expectation of g of x time expectation of h of y. So we can write expectation of e power t1 x time expectation of e power t2 y. So this is exactly MGF of x at t1. This is exactly MGF of y at t2. So therefore we have joint MGF of xy at t1 t2 equal to MGF of x at t1 times MGF of y at t2. Okay, fine. Next, here we have a general theorem. x1, x2, xk are independent if and only if joint MGF of x under bar at t1, t2, tk equal to product of MGF of xi at ti for I equal to 1 to k for all points t1, t2, tk in Rk, where x under bar is k dimensional vector of k random variable x1, x2, xk. Okay, we can easily prove it using induction on k. We already proved for a k equal to 2 in the above theorem. That is going to be our base case. Okay, fine. Next theorem, if x and y are independent, then MGF of x plus y at t equal to MGF of x at t times MGF of y at t for all t belongs to R. Okay, here the left hand side is not joint MGF. Here x plus y is univariate random variable. Think like a z equal to x plus y. Then I am talking about mz of t. It's going to be what by definition? Expectation of e power tz. What is z here? X plus y. Okay, let me start with the left hand side. Let me show that equal to right hand side. Okay, the left hand side mgf of x plus y at t by definition expectation of e power t of x plus y. This e power t of x plus y we can write e power tx times e power ty again by using independence, as this is a function of x alone, this is a function of y alone. We can write expectation of e power tx times expectation of e power ty. This is exactly mgf of x at t. This is exactly mgf of y at t. So we have mx plus y of t equal to mx of t times my of t for all t belongs to R. Okay, fine. Next we have a generalization. If x1, x2, xk are independent random variable, then MGF of summation of xi from I equal to 1 to k at t is product of mxi of t for I equal to 1 to k. Okay, we can easily prove it using induction on k. In the above theorem, we proved for k equal to 2. That is going to be our base case. Okay, we are going to use this theorem in the following way. If x1, x2, xk are k independent random variables having some known probability distribution, that means you know their MGF, that is mx1 of t, mx2 of t, so on, mxk of t known. Okay, and you are interested in knowing the probability distribution of summation xi from 1 to k. Okay, so what you do, you try to focus on this right hand side product. If this product turn out to be MGF of some known distribution, then you can say that this summation xi follows that particular distribution, because MGF uniquely determine its probability distribution. Okay, that's how we are going to use this theorem. Okay, fine. Theorem, let x1, x2, so on, xk are independent and xi follows binomial distribution with the parameters ni comma p for I equal to 1 to so on k. Then summation xi from I equal to 1 to k follows binomial distribution with the parameters summation ni from I equal to 1 to k comma p. Okay. Here, for each xi, we have same probability of success p. Here xi follows binomial distribution with the parameters ni comma p. That means xi denote the number of success in sequence of ni independent identical Bernoulli trials, each with the probability of success p. So this x1 plus x2 plus so on xk should denote the number of success in sequence of n1 plus n2 plus so on nk independent identical Bernoulli trials, each with the probability of success p. That's why the summation xi from I equal to 1 to k must follow binomial distribution with the parameters summation ni from I equal to 1 to k comma p. Okay. Intuitively, it is pretty clear. Anyway, we are going to prove it using above theorem. Okay. Proof. Here xi follows binomial distribution with the parameters ni comma p. So its MGF going to be 1 minus p plus p power t power ni for I equal to 1 to so on k. Because we know what is the MGF of binomial distribution. So we can write down MGF of xi like this. Okay. Now, from above theorem, MGF of summation xi from I equal to 1 to k at t going to be product of MGFs of xi at t for I equal to 1 to k, since x1, x2, xk are independent. Okay. Now, if you replace mxi of t with a 1 minus p plus p power t power ni, we end up with this product. This product will be simplified to 1 minus p plus p power t power summation ni from I equal to 1 to k. As we have a same base here, we simply add up exponent, so we end up with this. Okay, so this is the MGF of summation xi from I equal to 1 to k. Now, this one can be recognized as MGF of binomial distribution with the parameters summation ni from I equal to 1 to k comma p. Okay, and we know that MGF uniquely determines its probability distribution. So we can say that the summation xi from I equal to 1 to k follows binomial distribution with the parameters summation ni from I equal to 1 to k comma p. Okay. This theorem says that sum of independent binomial random variable with the same probability of success p will be again binomial random variable. Okay, fine. Next, corollary. If x1, x2, so on, xk are independent and xi follows Bernoulli distribution with a parameter p for I equal to 1 to so on k, then summation xi from I equal to 1 to k follows binomial distribution with the parameters k comma p. See, this directly follows from above theorem because Bernoulli distribution is a special case of binomial distribution. Here each xi can be seen as binomial with a parameter 1 comma p. So if you apply above theorem, we have n1 equal to n2 equal to so on, nk equal to 1. That implies n1 plus n2 plus so on, nk going to be equal to k. So from above theorem, we can say that the summation xi from I equal to 1 to k follows binomial distribution with the parameters k comma p. Okay, fine. Next theorem, let x1, x2, so on, xk are independent and xi follows Poisson distribution with the parameter lambda I for I equal to 1 to so on k. Then summation xi from I equal to 1 to k follows Poisson distribution with the parameter summation lambda I from I equal to 1 to k. Okay, we are going to prove it in a similar fashion. Okay, here xi follows Poisson with the parameter lambda I. That means MGF of xi going to be e power lambda I times e power t minus 1 for I equal to 1 to k, because we know what is the MGF of Poisson distribution. So we can write this. Now MGF of summation xi from I equal to 1 to k at t going to be product of MGFs of xi at t for I equal to 1 to k, since x1, x2, so on, xk are independent. So now if you replace mxit with e power lambda I of e power t minus 1, so we end up with this product. This product will be simplified to e power summation of lambda I from I equal to 1 to k times e power t minus 1. Okay, so this is the MGF of summation xi from I equal to 1 to k. This can be recognized as MGF of Poisson distribution with the parameter summation lambda I from I equal to 1 to k. Okay, so we can say that the summation xi from I equal to 1 to k follows Poisson distribution with the parameter summation lambda I from I equal to 1 to k. Okay, that means this theorem says that sum of independent Poisson random variables again Poisson random variable. Okay, fine. Next theorem, let x1, x2, so on xk are independent and xi follows negative binomial distribution with the parameters ri comma p for I equal to 1 to so on k. Then summation xi from I equal to 1 to k follows negative binomial distribution with the parameters summation ri from I equal to 1 to k comma p. Again, we are going to prove it in similar fashion here. Here xi follows negative binomial distribution with the parameter ri comma p. So its MGF of xi is going to be this p by 1 minus p plus p power t power ri for I equal to 1 to k, because we know what is the MGF of negative binomial distribution. So we can write this. Now MGF of summation xi from I equal to 1 to k at t going to be again product of MGFs of xi from I equal to 1 to k. Since x1, x2, xk are independent. Now if you replace mxi of t with this one, you will end up with this product. This will be simplified to this one, which is p by 1 minus p plus p power t whole power summation ri from I equal to 1 to k. This is the MGF of summation xi from I equal to 1 to k. So this can be recognized as MGF of negative binomial distribution with the parameters summation ri from I equal to 1 to k comma p. So we can say that this summation xi from I equal to 1 to k follows negative binomial distribution with the parameters summation ri from I equal to 1 to k comma p. Okay, this theorem says that sum of independent negative binomial random variable with the same probability of success p again negative binomial random variable. Okay, fine. Next, corollary, let x1, x2, so on xk are independent and xi follows geometric distribution with the parameter p for I equal to 1 to k. Then summation xi from I equal to 1 to k follows negative binomial distribution with the parameters k comma p. Okay, this directly follows from above theorem, because we know that this geometric distribution is special case of negative binomial distribution. Here each xi can be seen as negative binomial random variable with the parameters 1 comma p. So if you apply above theorem, here we have r1 equal to r2 equal to so on rk equal to 1. That implies summation ri from I equal to 1 to k going to be k. So from above theorem we can say that the summation xi from I equal to 1 to k follows negative binomial distribution with the parameters k comma p. Okay, fine. Next theorem, let x1, x2, so on xk are independent and xi follows gamma distribution with the parameters alpha I comma lambda for I equal to 1 to so on k. Then summation xi from I equal to 1 to k follows gamma distribution with the parameters summation alpha I from I equal to 1 to k comma lambda. Okay, here we have a same parameter lambda for all I. Okay, here again we are going to prove it in similar fashion. Here xi follows gamma distribution with the parameters alpha I comma lambda. So MGF of xi going to be lambda by lambda minus t power alpha I for I equal to 1 to so on k. Okay, this all makes sense from minus lambda to lambda. Fine, because we know what is the MGF of gamma distribution, so we can write this. Now MGF of summation xi from I equal to 1 to k at t going to be product of MGFs of xi at t for I equal to 1 to k, since x1, x2, xk are independent. Now if you replace mxi of t with lambda by lambda minus t power alpha I, we end up with this product. This product will be simplified to lambda by lambda minus t whole power of summation alpha I from I equal to 1 to k. Here we got the same base, so simply we add up exponents alpha I, so we end up with this. Okay, this is the MGF of summation xi from I equal to 1 to k. Okay, so this can be recognized as MGF of gamma distribution with the parameters summation alpha I from I equal to 1 to k comma lambda. Okay, so we can say that the summation xi from I equal to 1 to k follows gamma distribution with the parameters summation alpha I from I equal to 1 to k comma lambda. Okay, so this theorem says that sum of independent gamma random variable with the same rate parameter lambda, again gamma random variable. Okay, fine. Next, corollary. Let x1, x2, so on, xk are independent and xi follows exponential distribution with the parameter lambda for I equal to 1 to k. Then summation xi from I equal to 1 to k follows gamma distribution with the parameters k comma lambda. Which directly follow from above theorem because exponential distribution is special case of the gamma distribution. Each xi can be seen as gamma random variable with the parameters 1 comma lambda. So if you apply above theorem, here we have alpha 1 equal to alpha 2 equal to so on, alpha k equal to 1. That implies alpha 1 plus alpha 2 plus so on, alpha k going to be k. Okay, so from above theorem we can say that the summation xi from I equal to 1 to k follows gamma distribution with the parameters k comma lambda. Okay, so sum of independent exponential random variable with the same parameter lambda going to be gamma random variable with the parameters k comma lambda. Okay, fine. Next theorem, let x1, x2, so on, xk are independent and xi follows normal distribution with the parameters mu I comma sigma I square. Here the mean parameter mu I, variance parameter sigma I square for I equal to 1 to so on k. Then summation xi from I equal to 1 to k follows normal distribution with the mean parameters summation mu I from I equal to 1 to k and the variance parameter summation sigma I square from I equal to 1 to k. Again, we are going to prove it in similar fashion. Here xi follows normal distribution with the parameters mu I comma sigma I square. So MGF of xi at t going to be e power mu I t plus half sigma I square t square for I equal to 1 to so on k, because we know what is the MGF of normal distribution. So we can write this. Now MGF of summation xi from I equal to 1 to k at t going to be product of MGFs of xi at t from I equal to 1 to k. Since x1, x2, so on, xk are independent. If you replace mxit with this one, now you end up with this product, and this product will be simplified to e power summation mu I from I equal to 1 to k of t plus half times summation sigma I square from I equal to 1 to k times t square. Okay, so this is the MGF of summation xi from I equal to 1 to k, and again this can be recognized MGF of normal distribution with the mean parameters summation mu I from I equal to 1 to k and variance parameter summation sigma I square from I equal to 1 to k. Okay, so we can say that the summation xi from I equal to 1 to k follows normal distribution with the mean parameters summation mu I from I equal to 1 to k and variance parameter summation sigma I square from I equal to 1 to k. Fine. Okay. So this theorem says that sum of independent normal random variables, again normal random variable. Okay. Fine. Next, corollary. Let x1, x2, so on, xk are independent and xi follows normal distribution with the parameters mu I comma sigma I square from I equal to 1 to so on k. Then summation ai xi plus bi from I equal to 1 to k follows normal distribution with the mean parameters summation ai mu I plus bi from I equal to 1 to k and variance parameter summation ai square sigma I square from I equal to 1 to k. Okay, this directly follow from above theorem. We already know that when xi follows normal distribution with the parameters mu I comma sigma I square, we know that ai xi plus bi follows normal distribution with the parameters ai mu I plus bi comma ai square sigma I square. Okay, that much we know for all I equal to 1 to so on k. Now if you directly apply above theorem, you can say this. Okay, fine. This directly follow from above theorem, so it is the corollary for above theorem. Okay, next. Okay, now let us see what should be the probability distribution of square of standard normal random variable. Here is a problem. Find the PDF of x, which is z square, where z is standard normal random variable. Okay. We already know from the knowledge of probability distributions of transformation. When we have y equal to x square, we can write down PDF of y in terms of PDF of x like this. Fy of y equal to fx of root y plus fx of minus root y by 2 root y. Further, if you happen to know this fx is even function, this further gets simplified to fx of root y by root y. Okay. Here, the PDF of z we denote by var phi. Var phi of z is 1 by root 2 pi e power minus z square by 2 for minus infinity less than z less than infinity. As you can see, this var phi of z is even function. So the PDF of x in terms of PDF of z, that is var phi, going to be this. Fx of x equal to var phi of root x by root x. Since you know this var phi function is even function. Now var phi of root x going to be 1 by root 2 pi e power minus x by 2, and in the denominator we have a root x. I'm writing that. Now the same thing I can rewrite like this. Okay, feel free to verify, both are same. 1 by root 2 pi 1 by 2 times x by 2 all to the power of 1 by 2 minus 1 times e power minus x by 2. Okay, these two are same. The reason I am writing like this, because now I am going to realize this PDF as PDF of gamma distribution. Okay, now this root pi actually gamma 1 by 2, right? So let me write like this. So 1 by 2 times x by 2 all to the power of 1 by 2 minus 1 times e power minus x by 2 by gamma 1 by 2 for x positive, 0 for x less than or equal 0. This is exactly PDF of gamma 1 by 2 comma 1 by 2 distribution, right? So here x equal to z square, where z is standard normal random variable, follows gamma distribution with the parameters 1 by 2 comma 1 by 2. Here alpha equal to 1 by 2, lambda equal to 1 by 2. Let me rewrite the same PDF as follows. Okay, fx of x equal to 1 by 2 to the power of 1 by 2 gamma 1 by 2 x to the power of 1 by 2 minus 1 e power minus x by 2 for x positive, 0 for x less than or equal 0. Same PDF, I just rewrite like this. Okay, this particular gamma distribution going to be special one. Okay, here x is said to have chi-square distribution with 1 degree of freedom. The one is this one. Okay, this one. Okay, here is the notation. This is a notation. We read it as x follows chi-square distribution with 1 degree of freedom. Okay, fine. Theorem: let x1, x2, so on xk are independent and xi follows chi-square distribution with 1 degree of freedom for I equal to 1 to so on k. Then summation xi from I equal to 1 to k follows gamma distribution with the parameters k by 2 comma 1 by 2. Okay, here xi nothing but gamma 1 by 2 comma 1 by 2, right? Here chi-square distribution with 1 degree of freedom nothing but gamma 1 by 2 1 by 2. So each xi can be seen as gamma random variable with the parameters 1 by 2 comma 1 by 2. So here alpha 1 equal to alpha 2 equal to so on, alpha k equal to 1 by 2 and lambda equal to 1 by 2. So as a sum of independent gamma random variables, it is pretty clear that the summation xi from I equal to 1 to k should follow gamma distribution with parameters k by 2 comma 1 by 2, because the sum of alpha I from I equal to 1 to k going to be what? 1 by 2 plus 1 by 2 plus 1 by 2 k times it's going to be k by 2. That's why the summation xi from I equal to 1 to k must follows gamma distribution with parameters k by 2 comma 1 by 2. Okay. A gamma k by 2 comma 1 by 2 distribution is called chi-square distribution with k degrees of freedom. Okay, let me give a definition for this. Definition: if x follows gamma distribution with the parameters n by 2 comma 1 by 2, this special gamma distribution, okay, here this lambda is 1 by 2, okay, the gamma is n by 2, where n is some integer. Then x is said to have chi-square distribution with n degrees of freedom, okay, whose PDF we can write like this: 1 by 2 to the power of n by 2 gamma n by 2 x to the power of n by 2 minus 1 e power minus x by 2 for x positive, 0 for x less than or equal 0. Okay, so this is the PDF of chi-square distribution with n degrees of freedom. Okay, here is a sketch for PDF of chi-square distribution for 2 degree of freedom, 3 degree of freedom, 6 degree of freedom, 12 degree of freedom. Okay, the CDF of chi-square distribution, here x follows chi-square distribution with n degree of freedom. The CDF of x, what is the CDF of x? We integrate the PDF from minus infinity to x, but here the support of chi-square distribution only from 0 to infinity. Here we are integrating PDF of chi-square distribution with n degree of freedom from 0 to x, which is going to be area under the curve PDF from 0 to x. Okay, so one can actually perform this integral using integration by parts, but it's going to be tedious job as the n gets bigger, because you may have to do lot of iterations to do this integration. So usually we don't do by hand, we approach some software to get these CDF values. Okay, so here I have written a program, you can play with this. Okay, here this green shaded portion is the area from 0 to 13.59. So this area is 0.941. Okay, okay, I hope you can see this. Okay, now let me change some degree of freedom here. Let us say 5. Okay, this is the area with the 5 degree of freedom. Chi-square distribution CDF value at 13.59 is 0.9816. Let me change x to something 9.62. At 9.62, CDF value going to be 0.9133. So the area that is covered from 0 to 9.62 is 0.913. Okay, where x is a chi-square distribution with 5 degree of freedom. Okay, let me take okay. So the CDF value at 5.4 going to be 0.631. So area covered from 0 to 5.4 under this curve, which is a PDF of chi-square distribution with 5 degree of freedom, is 0.631. Okay, so like this. Fine. Okay, here is the notation. We read it as x follows chi-square distribution with n degrees of freedom. Okay, first of all, if x follows gamma distribution with the parameters alpha comma lambda, then we know that expectation of x will be alpha by lambda, variance of x will be alpha by lambda square, and MGF going to be lambda by lambda minus t power alpha, which makes sense from minus lambda to lambda. Okay, this is what we know about gamma distribution. Fine. Now chi-square distribution with n degrees of freedom, nothing but gamma distribution with the parameters n by 2 comma 1 by 2. Here alpha equal to n by 2, lambda equal to 1 by 2. So as a gamma distribution, we can immediately answer expectation, variance and MGF for this chi-square distribution with n degrees of freedom. Okay. So for this chi-square distribution with n degrees of freedom, expectation is going to be n and variance is going to be 2n, because what is the expectation? Alpha by lambda, right? Here alpha is n by 2, lambda is 1 by 2, so it's going to be n. And variance is going to be alpha by lambda square, right? Here alpha is n by 2 and lambda is 1 by 2 whole square, it's going to be 2n. Okay, and MGF is going to be lambda by lambda minus t whole power alpha. Here lambda is 1 by 2. So 1 by 2 by 1 by 2 minus t whole power n by 2. So this will be simplified to 1 by 1 minus 2t whole to the power of n by 2, which makes sense for t between minus 1 by 2 to 1 by 2. Okay, so that's why for chi-square distribution with n degrees of freedom, expectation is n, variance is 2n, and MGF is 1 by 1 minus 2t whole to the power of n by 2, which makes sense in the interval minus 1 by 2 to 1 by 2. Okay. Note, if x follows chi-square distribution with n1 degrees of freedom, y follows chi-square distribution with n2 degrees of freedom, and x and y are independent, then x plus y will follows chi-square distribution with n1 plus n2 degrees of freedom. Okay, because this chi-square distribution with n1 degrees of freedom nothing but what? Gamma with the parameters n1 by 2 comma 1 by 2. This chi-square distribution with n2 degrees of freedom nothing but gamma with the parameters n2 by 2 comma 1 by 2. As the independent gamma random variables with the same rate parameter 1 by 2, we can say that this x plus y follows again gamma distribution with the parameters n1 by 2 plus n2 by 2, that is n1 plus n2 by 2 comma rate parameter 1 by 2. So this is nothing but chi-square distribution with n1 plus n2 degrees of freedom. So this note says that sum of independent chi-square random variables again chi-square random variables. Here degrees of freedom add up. Okay, fine. Next, let x is a chi-square random variable with n degrees of freedom. For alpha between 0 and 1, a real number x belongs to R such that probability of x bigger than x equal to alpha denoted by chi-square alpha n. Okay, for this number, the area under the PDF from this number to infinity is alpha. Okay, such a number is denoted by chi-square alpha n. These values are used in many statistical methods. To get these values, one has to use software or refer to chi-square alpha n tables. These tables can be found in any statistics book. Okay. Okay. Here is the application. You can play with this. Here let me take n value 6, alpha value 0.050. Okay. As you can see, this yellow shaded region area is 0.05. Okay. This chi-square 0.05 comma 6 value is here 12.5916. That means area covered from 12.5916 to infinity under this PDF of chi-square distribution with 6 degrees of freedom equal to 0.05. Okay, so let me change alpha value. Yeah, 0.1. Let me take n equal to 5. Okay. Okay. Here, this yellow shaded region area is 0.1. Okay. So this chi-square 0.1 comma 5 value we got here 9.2364. That means area covered from this 9.23642 to infinity under this PDF of chi-square distribution with 5 degrees of freedom is 0.1. Okay, you can get this chi-square alpha n values like this through this application, or you can use some Python commands. Okay, next. So this is a table you can find in any statistics book. In this table, we are given chi-square alpha n values for some standard values of alpha and n values from 1 to 30. Up to 30 degrees of freedom we can get for some standard values of alpha. Most of the time we will be using chi-square alpha n values for these alpha values only. Okay. For example, if you want chi-square 0.01 comma 4 value, what you do, you go to the fourth row and the column under 0.01. Okay, so this is going to be the value. So 13.277. So area under the PDF of chi-square distribution with 4 degrees of freedom from this 13.2772 to infinity. This area going to be equal to 0.01. Okay, fine. Okay, next. The chi-square distribution often arises in practice as being the distribution of the square of errors involved when one attempts to hit the target in n-dimensional space when the coordinate errors are taken to be independent standard normal random variables. It is a widely used distribution in many statistical methods. Okay, let us see this by simulation. Okay, fine. In this program, I have taken 3 standard normal random variable. Okay, this line will give me million locations that we can hit when we try to hit the 0, 0 location. Okay, where the coordinate errors follow standard normal distribution. Okay, then here this error square going to be what? X square plus y square plus z square. When we try to hit the location 0, 0, if the location that we hit is x, y, z, then error square going to be what? The distance between 0, 0 to x, y, z. That's going to be x square plus y square plus z square. So this error 2 will consisting of million data points, which are these errors we make in million times, right? So I'm going to plot the histogram for this data for this million points using 50 bins here. Okay, and I'm also plotting the PDF of chi-square distribution with 3 degrees of freedom. Here, this is the chi-square random variable with 3 degrees of freedom. So I'm plotting its PDF here. Okay, because we know that this x square plus y square plus z square follows chi-square distribution with 3 degrees of freedom. Okay, because x square is a chi-square 1, y square is a chi-square 1, z square is a chi-square 1. Sum of the 3 independent chi-square 1 random variables is going to be chi-square 3 random variable. That's why I'm trying to plot PDF of chi-square distribution with 3 degrees of freedom. Okay, now let's see how it looks. As you can see here, the red curve is PDF of chi-square distribution with 3 degrees of freedom. The histogram we plotted here from the million data points that we got as the errors that we make in million hits. Okay, fine. So as we mentioned, this chi-square distribution with n degrees of freedom often arises in practice as being the distribution of error square involved when we try to hit the target in n-dimensional space, when we assume that errors we make in each coordinate are standard normal random variables. Okay, fine. Okay, let's do a problem. Suppose that we are attempting to locate a target in three-dimensional space and that the 3 coordinate errors in meters of the point chosen are independent normal random variables with a mean 0 and standard deviation 2. Find the probability that the distance between point chosen and target exceeds 3 meters. Okay, here we are trying to locate a target in three-dimensional space. Let's call it ABC target. Okay, so the errors we make in each direction to locate ABC are normal random variable with a mean 0 and standard deviation 2. Okay, here we have to find the probability that distance between point chosen and target exceeds 3 meters. Okay, fine. Okay, let ABC be the target in, let us say the point we have chosen is XYZ. Then errors we are going to make, the x1 going to be x minus a, x2 going to be y minus b, x3 going to be z minus c. These are the errors we make in each coordinate. Okay, so here it is given that this x size follows normal distribution with a mean 0 and standard deviation 4. So here mu is 0 and sigma is given 2, so sigma square going to be 4. Okay, let D denote the distance between point we have chosen and the target, and X denote the error in ith coordinate, which follows normal distribution with a mean 0 and variance 4 for I equal to 1, 2, 3. What is D actually? Distance between point we have chosen and the target. It's going to be under root x minus a whole square plus y minus b whole square plus z minus c whole square. Okay, it's going to be under root. What is x minus a? Error in direction 1, y minus b error in direction 2, z minus c error in direction 3. That's going to be x1 square plus x2 square plus x3 square. Okay, this is the distance between the point we have chosen and the target. So here we are interested in probability of d bigger than 3. Okay, now the d square going to be x1 square plus x2 square plus x3 square. Here xi is what? Normal random variable with a mean 0 and standard deviation 2. So here if I take the zi, which is xi minus mu by sigma, here mu is 0, sigma is 2. We know this is going to be standard normal random variable for I equal to 1, 2, 3. Then z1 square plus z2 square plus z3 square going to be chi-square 3 random variable, because z1 square of the standard normal what? Chi-square random variable with 1 degree of freedom. So this is chi-square 1, this is chi-square 1, this is also chi-square 1. Sum of 3 independent chi-square 1 random variables going to be chi-square 3 random variables. So z1 square plus z2 square plus z3 square going to be chi-square 3 random variable. Okay. Now here we are interested in probability of d bigger than 3. Okay. D bigger than 3 if and only if d square is bigger than 9. Okay. What is d square? X1 square plus x2 square plus x3 square. Here from this I can write xi will be equal to 2zi, right? That implies xi square going to be 4zi square for I equal to 1, 2, 3. Okay, so this is going to be 4z1 square plus 4z2 square plus 4z3 square. So if I take this 4 this side, I can write this event, I can write z1 square plus z2 square plus z3 square greater than 9 by 4. Okay, so we have to find probability of z1 square plus z2 square plus z3 square greater than 9 by 4. But what do we know about this one? This is a chi-square 3 random variable. So we have to find probability of chi-square 3 greater than 2.25. This 9 by 4 value 2.25. This we can write 1 minus probability of chi-square 3 less than or equal to 0.5. Okay, so this is nothing but CDF value of chi-square 3 at 2.25. Using software we can get this one 0.4772. Okay, so 1 minus 0.4772 going to be 0.5322. Okay, so this is the answer. This is the probability of distance between point chosen and target exceeds 3 meters. Okay, fine. Okay, let me stop now. Thank you.